Hey everyone, I'm here. I'm starting to see the attendees.
Yeah, hey, Shruti, Jimmy's here too.
Okay, great. Okay, I think we're starting to see people join, which is great. I'm going to unmute myself for the audience. I'm not sure whether we are already broadcasting or not. Chris or Fanny, can you confirm?
Yes, all the attendees are in listen-only mode, muted. So if anyone has questions, feel free to use the questions chat box. We will be monitoring that.
Got it. Yeah. Okay. Sounds great. Okay. So I am seeing people joining. Thank you, everyone, for sharing your lunchtime today with us. We'll just wait another 30 seconds or so and then get started. And like Fanny mentioned, if you have any questions, if you're having any trouble, feel free to write your question in the question box and we'll be monitoring that. All right, let's get started. And then as people come in, they can join us. Okay, great. So welcome everyone for a presentation on building decarbonization. Today, my name is Shruti Kasavekar. I will be presenting with my colleague, Amy Leedham. I'll do a brief introduction for the both of us, and then we'll dive in. So I am an environmental designer. I'm an associate director at Atelier 10 in the San Francisco office. Extremely passionate about the built environment and driving sustainability within the built environment. My colleague Amy Leedham, who will also be speaking today, is also working out of the San Francisco office. She's an associate in the San Francisco office, and she's also a registered architect. In addition to that, she also leads our carbon practice within Atelier 10's US office and has brought really great expertise in the field of decarbonization within the built environment, which we are going to share with you today. So I also would like to thank AIA Silicon Valley Code for inviting us for this presentation. This is a great topic to have a discussion on today. And we are hoping that by the end of today's session, you're able to feel a little inspired and maybe take home or take to your work a few strategies and a few pointers on how to implement decarbonization within your regular design process for buildings. So let's get started. All right. So for those of you who are not very familiar with Atelier 10, we are a firm of environmental consultants. We are extremely passionate about driving sustainability within the built environment and consult on a range of topics. We pretty much work across the entire building spectrum, from large single-family houses to master plans and everything in between. And we offer services in a pretty wide range, from environmental design to resilience and adaptation and planning to carbon management. So today's presentation, we are going to focus on decarbonization of buildings. And so the obvious question here, I'm sure, would be that of the many things that we could talk about, why carbon? And it's a pretty simple answer. Buildings are important within the conversation about climate change. We have the next 10 years to make a big impact on the way buildings use energy and emit carbon. We need to tackle climate change faster than ever. And if you have been keeping track of the IPCC reports, now is the time to make that change. So within the building sector, building operations and the building materials and construction play a very big role in the global carbon emissions. So this graph here is just showing that more than 40% of the global carbon emissions are associated with buildings. And so we have a large role as designers to play in managing carbon emissions associated with buildings. In addition to that, incidentally, like exactly a year ago, in early June last year, AIA passed a resolution, and it basically says, if you're not aware of this already, that it is extremely important to accelerate the decarbonization of buildings, and that AIA prioritizes this and would like to continue to push this topic until a zero net carbon practice is acceptable and is a standard practice. So now is the time for us to really think about how to integrate some of the decarbonization concepts into our business as usual thinking without considering that this is something that we only have to do on special buildings. More regionally, in California, you may or may not be aware of this, but essentially all our electricity is set to be carbon-free by 2045. This is one of the prime drivers why we talk about electrification, if you've heard that term, associated with reducing carbon emissions. In addition to that, more locally in San Francisco, the goal is to achieve net zero greenhouse gas emissions by 2050. And we are also on track to achieve 100% renewable electricity by 2030. Now, the interesting thing is that even the state of California has now acknowledged, which is the third section here, that we need to start thinking about carbon emissions beyond just burning fuels within your building. And the state agencies are therefore requiring that embodied carbon be also considered when thinking about decarbonization of the built environment. So what that brings us to is, what do we need to do now, and what is it that we need to tackle? So on the graph to the right here, you see two colors, yellow and blue. Both of those represent different types of carbon emissions associated with the built environment. The yellow represents embodied carbon emissions, and the blue represents operational carbon emissions. Our actions right now for the buildings that will be built for the next 50 years, for the next 60 years, are going to have a significant impact on what carbon emissions, what level of carbon emissions we are going to emit into the environment over time. So what you see here is that when a building is built, a decision is made, and the embodied carbon emission gets locked into the environment right now. So the time value of carbon of the decisions that you're making right now have an impact on the building long term. That embodied carbon gets baked into the environment and it remains there forever, which is this yellow bar recurring over time. The operational carbon emissions are slightly different. They might seem smaller in comparison to embodied carbon emissions for the first year. However, they recur year after year and accumulate over time. At the end of the building life, in 50 years down the line, both of those together are extremely important. Some early studies on these topics tell us that both of these together are probably going to weigh similarly, 50-50. However, in the next 10 years, which is when we want to make the biggest impact possible, embodied carbon emissions become way more important than operational carbon emissions, knowing that operational carbon emissions will continue to become important. So what we are going to do today, just knowing this, is we're going to spend a little bit of time talking about what is the definition of operational carbon emissions, what is the definition of embodied carbon emissions, and then we are going to look at how to integrate the approach for reducing carbon emissions for both of these areas effectively in your building design, and how some of the processes that we do already allow us to do it pretty effectively if we just pay a little bit more attention to what we're doing. So I'll begin by defining operational carbon emissions, and then we'll move on to embodied. So most of us are aware of several net zero energy definitions. There is a way to measure energy. We have seen and heard and read about site energy. We've seen and heard about energy cost, which is a more known metric for LEED, for instance. And then sometimes we also talk about source energy, especially in California, when talking about how much energy the buildings are using. All of these, in a way, are proxies for what the impact of the building on the carbon or the greenhouse gas emissions. So a true environmental way to reduce the impact, or the true way to reduce your impact on the environment, is to look at the carbon emissions instead of looking at the source energy, site energy, or energy cost. They're all trying to do the same thing, but ultimately what matters is carbon emissions. So when you think about it, the old way to quantify the impact of operational carbon emissions was to understand how much energy your buildings were using a variety of tools. Then knowing which grid or which fuels you are utilizing within your building, and applying those emissions, greenhouse gas emissions or carbon emissions factors to your energy use to ultimately understand what your greenhouse gas emissions are. However, what we are seeing now is that the time of use of when the energy is consumed and when the carbon emissions are actually emitted matter a lot. So what you see here is a heat map that shows a typical day on the left from 1 a.m. to midnight, and a typical day of each month. And the first square here is the building energy use, then is the energy cost, and then the carbon emissions. The green color indicates that it's a lower value the red is a higher value, which means green is better and red is worse. So you can quickly, when you put these three metrics side to side, you start to see immediately that when a building is actually consuming energy, what time of the year, what time of the day, may not be reflected correctly in the way the actual emissions, when the actual emissions happen. So this basically means that you may be designing your buildings to do one thing with the hope that it reduces the energy use and ultimately carbon emissions. And when you're reducing your energy use, you are partly doing that, but it's not exactly having the effect that you want because the carbon emissions happen at different scales at different times of the day. So what you see here on the graph is the varying amount of carbon emissions by hour for a typical day. And you'll notice here that the carbon emissions actually peak in the later part of the day and they flatten out in the earlier part of the day. And so really having the ability to move your building use, building energy use or your building loads to flow with this carbon emission profile is ultimately very important to be able to manage your carbon emissions effectively. So the new way to think about carbon emissions, the operational carbon emissions, is to continue to think about energy use. It remains an extremely important criteria. But then to add another layer to it and to understand when that energy is being utilized and whether our strategies allow us the flexibility to move the energy use of the building to the time of the day, to the part of the year when our electricity is the cleanest, and then apply the conversion factors to have the maximum impact on your operational carbon emissions. So there are two things that become extremely important when we're talking about operational carbon emissions. One is the energy use, which we are fairly aware of on how to tackle. And the second part is the time of use, which will show you in this presentation on different ways to tackle that. That is ultimately going to impact your operational carbon emissions. So I'm going to pass on to Amy now, who's going to talk about embodied carbon concept in a similar way, and then we'll take it from there. Amy, all yours.
Yeah, great, thanks. Am I able to? Yes, perfect. So I think it's helpful, just similar to Shruti was just doing, provide a little bit of an introduction to what embodied carbon means. I know it's a much more popular term over the past couple of years than it was previously, but fundamentally, when we say embodied carbon, we're really talking about CO2 equivalent emissions, so all greenhouse gas emissions associated with the extraction, manufacturing, transportation, kind of maintenance and replacement, and then also ultimately the disposal of building materials. If you go to the next one, you can look at that in another way. Yeah, perfect. This is the kind of more formal graph that shows all of the different life cycle stages as they're defined by the ISO standard. And so there's a lot of different terms, especially globally, around carbon. So when we say embodied carbon in the US, we're talking about, again, the entire life cycle of the building and the building materials associated with them. In the UK, embodied carbon is actually just talking about what we have highlighted in red here, which is upfront carbon. And that's the carbon, embodied carbon that happens before building occupancy. And so that's, again, this extraction of materials, the energy required to manufacture and transport those materials to the construction site and install them. And then operational energy and operational water use are excluded from the term embodied carbon, but if you're going to do a whole carbon assessment of a project, they would be included. So there's a lot of different kind of facets, but hopefully a graphic like this is helpful to understand what's included. I think the other key thing is it's called embodied carbon, or a whole building life cycle assessment is the analysis procedure, but it's not actually the whole building in most cases. So for example, the LEED life cycle assessment credit that I'm sure a lot of you are familiar with that addresses embodied carbon is actually only accounting and addressing materials in the structure and enclosure. Everything else is excluded. Today we'll talk about interiors quite a bit because it is quite important, and so we tend to include that when we're looking at analysis, but building systems, site work, and landscape are almost always excluded. And one of the main reasons for that is kind of the lack of availability of data on the components that contribute to those systems. So hopefully as time passes, more data will be available and we can start to fold those into our analysis. And then I think the other thing that's exciting about this field is that it is starting to be addressed in rating systems and regulations. So a couple examples, again, I mentioned this whole building life cycle assessment credit in LEED, which is worth up to 4 points. The ILFI has a zero carbon certification, which addresses both operational and embodied carbon, which is pretty cool. It doesn't mean there's this other pathway for projects to really focus on carbon, and they don't necessarily have to do the whole living building challenge, but they can just focus on this one issue. And then as Shruti mentioned, California has some regulations around embodied carbon. Some countries in Europe are expected to be implementing kind of total limits on the embodied carbon that's allowed per for projects to get building approval. So this is a fast-moving and rapidly developing area of the built environment. And I think the other thing that's really helpful to understand, and you know, this applies to operational energy and operational carbon as well, but you know, there's the LEED credit, which I mentioned, and again, I know a lot of us focus on the benefits that we can get from doing some type of analysis on something like embodied carbon for LEED points, but it is really just another kind of facet of the design process. It's just another driver to consider throughout the entire process, and I'm hoping that the content we're sharing today will highlight that and really make that clear. But you know, much like we would address any other design issue throughout the design process for embodied carbon, you know, early on we want to understand our context. We want to identify what the biggest carbon drivers are, make those big decisions around things like massing and structural system selection early, and then kind of continue to optimize as we move through the design process. And then for the LEED credit, the only things you really have to do are the whole building LCA, the analysis portion, and then the documentation. But I think as a design topic, it goes far beyond what the LEED credit requires at the moment. And then I think there was one more, yeah. And then I think it's helpful to just kind of get a sense of you know, how embodied carbon is distributed through a building, and how kind of some structural types can compare to each other. I will caveat this to say this is highly regional and also very dependent on project specific. So this comparison isn't necessarily true across the board, but I think it's helpful to see that, you know, the structure, the above ground structure is really a very critical component of the embodied carbon of a project. Foundation, also very important. And then enclosure, it's going to vary. And then this doesn't even talk about interiors. Like I mentioned, we'll talk about that a little bit later.
All right. So, so now that we've introduced both the concepts, what we wanted to discuss today is how to integrate the design for carbon neutrality in regular design process and what are the types of concepts that we should be looking at in order to successfully do so. So here's a path to a carbon neutral building design. It often starts with the conventional design here on the far left, and there are several things that are within the control of the architectural community, within direct control, that can be influenced pretty easily, I would say, within the design process, given today's market and tools. That consists of looking at the regional context to understand what is it that is going to make sense for the particular region where your building is. And then looking at the types of concepts that we have always been talking about for any high performance projects, with an additional layer of what those concepts would do for embodied carbon and time of use. So looking at the massing and the envelope, looking at the comfort conditioning systems and the indoor quality, looking at the active systems, and finally, the renewable energy production. Now, when we talk about building design, we as sustainability consultants, and I'm sure many of you here on in this meeting today as well, would like to see additional areas to be included in this narrative, and that often moves this discussion from the design of the building to the operations, and then including other systems which are not exactly related to architecture but play an extremely vital role in the functioning of the building, which are the water systems and the landscape. And then finally, we're actually going to talk a little bit about offsets today, on why offsets are also critically important in being able to reach the carbon neutral goal. The scope here can be widened even further than that, and beyond the physical boundaries of not just your building, but also beyond your site. There are other issues such as the procurement of resources within your buildings that can be lumped into this boundary to make this more meaningful, and then that sort of gets into a more carbon positive process. So today we are going to focus on what is directly in the control of designers, and I'll start with the regional context first. So here in the United States, the regional context that drives the operational carbon decisions on buildings are two. One is the upcoming, or in many cases already implemented, natural gas ban that you've been hearing in the newspapers, and I'm sure encountering on your project as well. And in addition to that, understanding the variability of the grid emissions for your region. Not all grid regions are made equal. Some are more intensive than the others. So even if you think that you're in California, does not mean that you're getting the same clean electricity for the entire California. It totally depends upon which regulatory agency you are under, and how that allows you or your utility to, or your building's utility to get electricity. So as a result of that, now expanding this a little bit beyond California, what that means is the conversation around decarbonization in California specifically, because of the high penetration of renewable energy in our grid, it directly translates into electrification of buildings. So in California, if you're designing a building, you can safely say for the most part that now or in the very near-term future, decarbonization is going to equate to electrification of buildings. However, that is not the case across the entire America. And in fact, if you see here closely, which is what this graph is trying to show, is that it is only in California right now and in certain regions in Northeast United States where electrification instantly right now at this time makes sense. Decarbonization has a very different meaning in other parts of the US and definitely in the other parts of the world. Go ahead, Amy.
Yep, sorry. Yeah, and then in terms of regional availability and kind of applicability of materials, so switching over to the embodied side of things, you know, we'll talk about mass timber today, and I'm sure everyone's kind of tuned into the buzz around mass timber as the kind of be all end all savior of the building industry. But the reality is, you know, the regional availability of that material is somewhat limited at this point. So this is just a map of buildings that are in design, but the reality is the manufacturing and production of mass timber products is fairly limited to the Pacific Northwest, and then some in the Northeast and kind of Canada and the US as well. And you know, manufacturing facilities are expanding due to demand, but it's not quite caught up yet. And then similarly, if we look at some of the main strategies to reduce the embodied carbon impact of concrete, so using post-consumer recycled materials like fly ash or slag is also highly regional. So we're having actually issues with some projects getting access to fly ash because it's a byproduct of coal power plants, and as those plants are getting phased out, that material becomes less available. So that's a good for many reasons, but it also means that then we're having to rely on cement. And so I think it's just important to consider the regional context and the availability of materials, you know, when you're kind of making some of these early stage big design decisions.
Right. So having that regional context on what is it that is going to matter for your specific area in which you're designing your building is extremely important, and that pretty much narrows the options on what can be done or what is feasible for your building. Then the next part is the massing and the envelope and the resulting indoor air, indoor quality and the comfort conditioning from the architecture. So these concepts you may have seen before, and the idea here is to continue to do the things that we have been doing for high performance buildings. They are exactly the things that are also going to be needed for decarbonization. So here, what you see on the left is an energy end use, operational energy end use split for a typical office building in California, here actually in the Bay Area. And what you see here, these little green arcs here are showing all the end uses that can be directly influenced by architecture. So put together, there is about 30 to 40% of the building's energy use that can be directly influenced by architecture. And if you remember in one of the earlier slides where it showed that the energy use plus the time of use aspect of that energy use is going to influence your carbon emissions. This is the range of impact that architecture can have. On a similar note, for embodied carbon emissions, the structure by itself constitutes to about 45 to 60%. That's a very large percent of embodied carbon emissions. So the decisions that are made through the basic principles of the floor plate design and the choice of structural systems, etc., that we are going to get into in a minute, they can have extremely large impact on embodied carbon emissions up to 60% and up to 40% on operational emissions.
Yeah, so diving into that structural system selection issue. Obviously, the design of the structural system is up to the structural engineer, but architects have a lot of influence in advocating for specific structural systems and helping in terms of, as Shruti mentioned, things like building massing and floor plate depth and heights and all of these types of things that do actually influence the type of structural systems that are applicable and how they can best be optimized. So I think the first one to talk about is the application of mass timber. It's a huge buzz topic at the moment, and I think I could spend hours and hours talking about it, but I'm trying to synthesize it into a few key points in a few minutes. Here is, yes, mass timber has the ability, has the potential to have a very significant impact on reducing the embodied carbon of a building. So the graph on the right is showing that just by replacing the primary superstructure from steel on the left to mass timber on the right, we're reducing the embodied carbon by 39%. And a big part of that is just because CLT is the primary type of mass timber that's being used here, drastically reduces the contribution of the above grade structure. You know, they have comparable strength to concrete or steel, but they're at a fraction of the weight, which also then reduces the kind of size of the foundation as well. So there's a whole lot to dive into around how to, you know, use CLT in a project. But I think the other thing that I want to hone in on is the contribution of sequestration. So one of the reasons that wood is called a carbon neutral design material is because when the tree is living, it's absorbing carbon and storing it in the wood. And that carbon stays stored until the wood is disposed of. And so a few key points are and that's called sequestration. And so this graph on the right here is actually showing the embodied emissions reductions, not accounting for that sequestration benefit, because there's a lot of questions about how to do that well. And it's one of the fastest kind of growing areas in the embodied carbon life cycle assessment world. So we always like to see, okay, let's take that carbon sequestration piece out of the equation first and just see what we can do and how we can reduce carbon just with the material efficiency of something like CLT over steel. But if you do, make sure to source sustainable timber and then also try to address what was going to happen to that timber at the end of its life. Obviously, you can't guarantee that it won't be burned, but there are plenty of ways to set up your design for the kind of highest and best reuse of that timber when the building reaches the end of its life. Then we start to be able to account for that sequestration benefit. And that's the graph on the left. So in this case, we go from a 39% reduction to a 74% reduction in embodied carbon emissions when we account for sequestration. So yes, you know, if it's sustainably sourced timber and, you know, you're accounting for end of life emissions, there's this much bigger impact, but it's still across the entire building. Using mass timber alone isn't going to get you to a carbon neutral building. And I think that's kind of the key. Those are the key points to make here. We move on to the next one. I won't go into too much detail. There's obviously a lot of hyper-regional or hyper-local limitations to the applicability of mass timber. The graph I actually just showed ended up having to add a decent amount of steel back into the lateral structural system due to the building code, but it is advancing quickly, and it's becoming easier to do mass timber buildings around the US. That being said, mass timber is still probably, you know, a special case. It's not the norm. And so how do we work with the structural systems that we tend to see, concrete being one of the primary ones in the Bay Area? And this is just an example of a project that had a very massive concrete structure, and there's a lot of opportunity to reduce embodied carbon of concrete, especially in the Bay Area. We have really sophisticated concrete manufacturers who are really great to work with throughout the design process to optimize the mix design specifically in each of the different locations. That's the kind of granular level that it's helpful to get to in order to understand the schedule, the strength, the other aesthetic requirements of the different mixes throughout the building, because they're obviously not all going to be the same. And this exercise was just looking at the biggest opportunities to replace cement in the concrete with either fly ash or slag in this case, to reach a overall target of 20% reduction. So there's a lot going on here, but I think the key points are starting this discussion early with the structural team, and then following through with the contractor to make sure if there are any schedule impacts, they can get folded in before it's an issue, and then engaging directly with the concrete suppliers and kind of implementing the targets and the mix designs into the specifications is a way you can achieve really significant embodied carbon savings by just focusing on concrete.
All right. So those are some of the the early on discussions and interventions that can be done to manage and reduce the embodied carbon emissions. Now, moving on to the operational carbon emissions, the very best case of a building's way to reduce operational carbon emissions would be to not use energy, or to minimize that energy use as much as possible. So it starts with some of the concepts that we all are quite familiar with on investigating into the passive functioning of the building. That starts with looking at different massing options, takes into consideration orientation, the access to daylight and natural ventilation, and now with this added layer of time of use, also looking for the best potential to integrate renewable energy generation within your building massing. So this example here is just showing a massing comparison of two early options. Similarly, here, this is showing some more details on how the passive functioning of a building can influence not just how the building is shaped, but also the size of the floor plate and where some of these structural systems that then influence the embodied carbon emissions go. So having narrower buildings with more facade area, or if that is not possible, having strategic punctures within your floor plate to be able to integrate both daylight and passive conditioning opportunities are some of the most important interventions that can be done to be able to reduce your energy use, as well as control the time of use when the energy is actually used. In addition to that, once sort of the shape of the building, the massing is figured out and the right interventions are considered there, the next bit is the building skin. So what you see here are the operational carbon drivers that the building skin can influence. So the building skin has an extremely important role in figuring out how much daylight the building can use on an annual basis, as well as the peak solar gain that the different spaces are going to see, and therefore the role of active systems in your building. In addition to that, there are other extremely important criteria, not directly related to the operational carbon drivers, but still quite important, which is the actual functioning of the space from a visual comfort perspective, as well as the views to the outside and the connection back to the environment. So here's an example of looking at the building skin really in a detailed way in an urban setting. This is 633 Folsom in San Francisco, and this is for this project we looked at the incident solar radiation falling on this urban site pretty extensively, and determined the type of horizontal and the vertical shading. It ended up being a combination for different areas of the building facade. So at a very primary level, the design of your external shading system plus your glazing properties is going to determine how much peak solar you are contributing to the space, and therefore enabling low energy buildings.
Yeah, and I think extending that, you know, the design of the external shade system to start thinking about the embodied carbon, right? Because you're adding this physical element to your building, and it's going there for, you know, many reasons, one of which being operational carbon, energy/carbon reduction, thermal comfort, visual comfort, so many benefits to an external shading system, but expanding how we think about that to include the operational carbon associated with the material that's required for that shading system. So, you know, and the hotter the climate, I think the kind of bigger the impact is going to be. But from an embodied perspective, this is just an example. This project is a very large kind of glazed facade area, really focused on employee wellness and daylight and views. But then this also included a very extensive shading system to control that solar gain, just like Shruti was just mentioning. And that was a key part of the energy efficiency strategy. And initially they were considering metal mesh. It's very common. You know, it can be very beautiful. You can do a lot with the patterning on the mesh, lightweight, all of these things. But it was such an extensive part of the envelope system that we proposed switching that out to be wood. So in this case, just when you isolate for the enclosure aspect, that results in a 19% reduction in embodied carbon, and across the building, that's a 5% reduction in whole building embodied carbon. And 5% may not sound huge, but keep in mind the LEED credit, 5% reduction is worth 2 points. And it's still 1.7 million kilograms of carbon emissions that's being saved through that materiality change. So again, the idea is just to kind of like expand the box of the issues that you're considering when making some of these kind of key architectural design decisions.
Right.
And then, you know, moving from enclosure into interiors, I mentioned the importance of interiors and embodied carbon across the whole building, and how it kind of gets overlooked, especially in the LEED credit. And I think here's a really good example of why and how important it is. So this is a Bay Area office building, and for this project, the interior worth almost 25%, almost a quarter of the whole building, whole life cycle embodied carbon, which is quite significant. And the reason for that is, you know, yes, there are fewer of those materials than the kind of huge mass of concrete you might have in the structure, but they're getting replaced a lot more frequently, right? So concrete and steel are in there for the life of the building, 50, 60, 75 years, however long it is. Interior materials, especially finishes, are getting replaced 5, 10, 15 years. They're getting replaced several times throughout the life of the building. And as architects, obviously, that's where you have a huge sphere of influence over what gets selected. And how much influence does that really, you know, how does that translate to embodied carbon reductions? I think this is a great example. You know, this project was also really prioritizing healthy materials. And so this is a case where really prioritizing for the material health as well as embodied carbon. We focused on a few key top categories. So the combined kind of optimization, if you will, product selection, of gypsum, ceiling tile, and an interior insulation. So looking at the embodied carbon of specific products and choosing the lower option, that was about a 1% reduction across the entire building. Paint is a very, very embodied carbon intensive product and gets replaced quite frequently. So again, selecting products with low embodied carbon compared to their comparable counterparts, that was an additional 2% reduction. And then the most impactful for this project was just carpet tile. And so again, going through this exercise of selecting specific products, comparing the embodied carbon intensity of different carpet products and selecting the lower ones, that was a 6% reduction. And this is across the entire building. So the carpet in this project is actually even more impactful than the shade on the previous example that we just showed. And when you combine them all together, you're at a 9% reduction across the whole building. So that's very, very significant. And again, it's product selection. And in the end, all of these products were cost comparable to the ones that they were replacing. The contractor did a detailed exercise. And I think it's really exciting how much influence product selection can have on embodied carbon.
Right. So then sort of translating this back to, again, operational emissions, the choices that are made on the space layout, and the more we are able to eliminate systems, helps us not just in reducing the energy use of the building, but also in reducing the embodied carbon emissions. Here showing the interior space design layout influenced by the availability and the access to daylight throughout the year. So the purple being the zones which are most appropriate for workspaces. So the other sort of layer, which is very unique to California and specifically in the Bay Area here, is the passive conditioning potential. So the graph here is basically plotting the outside air conditions throughout the year from, and then banded here between 8 a.m. and 6 p.m. And all the black dots that you see here is when the conditions are perfect for any sort of passive ventilation. And the blues are when it is either too hot or too cold to be using that air. So what this is showing is that majority of the year, 60% of the time, we have conditions that are very conditioning. Now, passive conditioning cannot be just applied onto a project as an afterthought. There are opportunities within projects that can translate into beautiful designs based on how this concept of passive conditioning and thermal variability can be explored. So the first step there is to understand that the way humans feel about space and the environment is different. They are taking cues from the immediate environment, whether they're outside or in an atrium or a workspace, a gathering space, or a densely occupied space. People are expecting different conditions for all of these spaces, and treating these spaces exactly the same is no fun. So there's a huge opportunity to think about thermal variability and understand how the conditioning criteria and the lighting criteria can be expanded and tweaked in a way to create different experiences from the outdoors to the inside. So an example of that is the Uber headquarter project with Shop Architects, which has this Solarium, which has you may have seen this already, but it essentially has this transition space between the interiors and the exteriors that spans the entirety of the building facade, of both the building facades. And the idea here was to create this space that is an in-between experience of the outside and the inside, which meant that it required the architectural team as well as us a really good understanding on how human body is going to perceive environments in cold outdoors, hot and sunny indoors, or neutral outdoors. And some of the ways in which thermal variability was translated into design strategies here was to sort of look at that volume and the materiality associated with that volume first, and then layer in specific strategies that you would use in any buildings that are suited for either passive ventilation or daylight conditions. In this case, having access to this entirety of the facade, which meant that we could have operable windows and shading located in the habitable zones embedded into the design. And then where it was absolutely needed, supplementing it with active cooling to a very limited extent. What this resulted in is not just a space that is naturally ventilated and that is differently designed, but really a beautiful buffer between the outside and the inside that is a real transition between the two environments and allows for a very unique thermal experience. In addition to that, because of a very different architectural take on this unique space, it also allows this building to achieve high levels of energy savings, because you're taking out all that energy use that otherwise you would have spent in not just conditioning that entire space, but also adding layers and layers of shading systems and whatnot into the building, and therefore also increasing the embodied carbon emissions associated with the building. So now I'm going to transition into sort of the last piece here, which is there is a lot to do with the architecture, as we saw, understanding the regional context. There's a lot that the architecture can shape. And then how that influences the active systems within the building and the renewables within the building. So important to note here is that all the decisions, all the strategies that we just discussed are directly influential in determining what kind of active systems can be applied to a building. So showing here is basically a range of mechanical systems that can be considered for a project, from really low energy systems like a radiant slab, which is quite passive, to a more typical VAV system and everything in between. And then the type of strategies that can be integrated into the architecture to be able to get to a point where a true low energy system can be designed. The last part here, and we've very specifically sort of deep focused on the systems discussion in this presentation, although it has a very large impact on how ultimately the operational carbon emissions profile is going to look for the building. But because we wanted to focus on the architecture more than the systems here, just the last layer is that unless the active systems are enabled to be able to be leaner, smaller, and right-sized, it is almost impossible to tackle the operational carbon emissions in a way that takes us to our carbon neutrality goal. So in California, we are not just dealing with operational carbon emissions as a metric, but we are also dealing with Title 24. We are dealing with maybe utility cost savings for other purposes like LEED. And then in addition, now we have started to fold carbon emissions into this conversation. And there are options out there that fit the description, that allow us to reduce energy use, reduce energy costs, and also reduce carbon emissions at the same time. It does require that next level of investigation, and the starting point for that is a high performance, low energy active system. So once we have these active systems in place, then traditionally the way we've understood the role of renewable energy systems in a building is to have an on-site renewable energy system that is basically doing a balance between what is between the amount of energy that is being imported into a building and the amount of energy that is either consumed in your building or exported back. And traditionally, the way we've looked at it is on an annual basis, looking at these together results in a net zero energy building. Well, that's great. And I think it still sort of gets us to a high performance building. But again, it's going back to some of the earlier discussions on why time of use really matters, is because if we start doing this calculation on an annual basis, your building may end up being a net zero energy building, but certainly not a net zero carbon building or even a carbon neutral building, not even close to that, unless you understand the time of use concept. So the next generation thinking here, to be able to tweak the time of use, is to not just design a low energy building that has some renewable energy source to it, but also to add resources into the building that allow that manipulation of time of use. We've been looking at batteries in a lot of cases to be able to tweak the time of the day when energy is getting utilized within the building versus getting stored in the battery to be then utilized at a later time of the day when the grid is really dirty. This we found is the most effective way to balance out the carbon emissions over time. Now, keep in mind that this will only work when you have enough renewable energy to actually feed your building. The cleanest way for the on-site renewable energy to be consumed is to be utilized in your building directly, at least for California. For other regions where the grid is dirtier, it might make sense to store it into batteries.
Yeah, and then again, this is an additional system that we're adding on to the building, and it has a very clear operational impact, but what's the embodied impact of that? So just really quickly, this is for a project in California. The embodied emissions are represented of the PV panels are represented here, and that kind of is spent, if you will. It's an investment, right? A carbon investment, and that's spent during construction, and that's kind of locked in. And then once the building is occupied and is started to operate, you save a certain amount of energy and carbon each year because of those PV panels. And so basically what this graph is showing is that it's going to take 3 years for those PV panels to pay back themselves in terms of carbon. And then starting at 3 years, the carbon savings of those PVs can start to offset the operational emissions. And so it is kind of delaying the operational impact, if you will, of those PVs. But it is a really short payback period. It shows that in California, even with our really quite clean grid, that's a really short payback period. And in other parts of the country where the grid is dirtier, that's probably, or it is definitely going to be an even shorter payback period. So it's still very worth doing on-site renewable. And then just to wrap it up, in terms of carbon offsets, this is the kind of one of the last big steps to get to neutrality. I think it's really important to quantify and include the embodied emissions of your project. Like we said, those are locked in. You can reduce them as far as possible through your material selection, your structural system selection, but they are still getting spent, they are still getting emitted, and it's important to offset them. It's also really valuable to offset the emissions associated with a project annually. So this is probably more of an owner related topic, but you want to offset your operational emissions based on the actual energy you used each year, not based on what you think you might use over the next 20 years. And then when selecting, your offsets, they're not all created equal. So additionality is really important. So for example, putting new PVs on your building, you are creating a new renewable resource that is offsetting, or funding a new renewable resource somewhere else that is getting built because you paid for it, or because the owner paid for it. That's additionality. So just buying some things that already exist isn't super helpful to actually offsetting the emissions associated with your project. And then I think our last slide to close it out is, you know, there's a whole lot that we didn't get to talk about today in detail. You know, operations, having operational practices in place is really critical. Addressing other aspects of the project, such as water use, the landscape, also really critical to true carbon neutral design. But those are kind of, keep an eye out for those opportunities. Those are the pieces of that are kind of the forefront, the frontier, the next frontier of carbon neutral design, if you will. I think that was the end. So we made it.
Yeah. Yeah, so we made it. Unfortunately, I know that we don't have enough time for questions. I can stay here for a bit longer if anyone has any questions or discussions. Otherwise, we are very happy to share our contact information and would love to answer any of your questions or comments through email or phone call, also whatever works for the people here. But I'll open it up for questions if anyone has any.
Yeah, there's a few in the chat box that I've been kind of, or in the questions box that I've been responding to. But Shruti, maybe you want to expand on. Yeah, there was one question that I provided an initial response to, but it might be worth having you respond to verbally. So the question was, there's a school of thought that says that an all-electric building that sources its energy from 100% renewable energy supplied by the utility is carbon neutral. What are your thoughts on energy efficiency versus carbon neutrality? And what I said is, you know, we still advocate for energy efficiency and peak load management because that's a really big part of what helps the utility remain 100% renewable. And we still advocate for on-site renewables if feasible to enable grid independence and resilience. But I'm sure you have more to expand on there.
Yeah. And yes, I think that's absolutely right. I think I would like very strongly disagree that if just because we are getting all the energy from which is 100% renewable from the grid, it means that we can do whatever on our building level. That is so not true until we know exactly how the electricity that we are consuming at this moment are from a renewable energy source. And the only way to actually know that is when you have a PV system or on-site renewable energy system sitting on top of your building that is feeding your building. There is no way for the electricity grid, as with the technology that we have right now, there's no way for the electricity grid to be able to react like completely with renewable energy sources. There will always be some sort of natural gas backup, some marginal plants that are natural gas, or in some cases maybe even nuclear, to be able to ramp up the electricity and to be able to cater to the very uncertain demand of electricity that is imposed on the grid. So I do not see a technology that is out there right now which will allow us to basically say that everything is renewable, therefore energy efficiency does not matter. Energy efficiency matters more than ever right now, especially when paired with embodied carbon emissions. Let me take, somehow I can't like make this.
Well, the other two
oh, there you go. Okay.
Questions, they've already left, and I did respond when they were off, so I think we're good.
I see. Okay.
Unless someone has any other questions.
Okay.
Great. Well, thank you, everybody.
Yeah, thank you, Shruti, and thank you, Amy, for taking your time today. And these are very valuable information. And we will make the recording available. Yeah, just look out for the next code event. Thank you, everyone.
Thanks all. Have a good afternoon. Bye.